Hello students, welcome back. Let us go back to chain rule, and we had been doing some exercises regarding the chain rule. Goes like this: step 1, derivative of the outer function; step 2, inside stays the same; and step 3, the derivative of the inside come here, out here like a dangling chain, not the inside. That's the essence of the chain rule. We usually say outer function part, blue; inside stays the same, red; and then the chain part. We went through several examples here. Elementary example that you just put chain rule and then that's it. You're going to see some examples like these in the exercise set, but in the exam, rarely, because that's too elementary. We're going to see some problems like these that you'll have to use chain rule twice or maybe more. And a lot of these, the problems that you have to combine product rule, quotient rule, and the chain rule possibly multiple times. Now let's work out some second derivative problem. And I have a confession, I rarely write these kind of problems because second derivatives usually make the problem too complicated unless the problem is really well designed, in that case too simple. And then there are some good problems intermediate, but they're rare, so it's kind of difficult to write exam problems regarding the second derivatives. But I have done those before, so let's work out some rather exceptional cases, typical cases where we have some nice problems, but these kind of problems are relatively rare. Okay, exponential function always stays the same. And then we have to multiply the derivative of the inside, right? Let's multiply the derivative of the inside. You see, this is the first and the second part, and then we multiply the derivative of the inside. 6x minus 2. And that is the derivative computation. You can switch the order if you want to. I decided to keep it as is. Now let's go over to the second derivative computation. Now this is going to be a product rule. Outer structure is product rule, and then we have to work out something inside. So here you go. U prime v plus u v prime. Okay, that is u prime and v staying the same, and u, the exponential part, staying the same. And v. That's going to be the outer structure. So we have to get these ... filled out. And shall we work out? Okay, u prime, it's a little bit complicated, so let's keep it a little bit later. This is easier, right? The derivative of 6x minus 2. Let's do that one first. The derivative of 6x minus 2 is just 6, so that takes care of the second part. How about this first part? It's an exponential function, so it always stays the same. And then by chain rule, you have to multiply the derivative of the inside, which is 6x minus 2. So in the end, what do you get? We have, 6, and then the exponential plus 6x minus 2 squared times the exponential, or even further, you get 6 plus 6x minus 2 squared times the exponential if you factor those out. The last factorization is not really necessary, but if you go over to chapter 4, there will be some problems that will require last factorization, and that's why I did it. As for simplifying from here to there, even though I do not require simplification, this is rather elementary simplification, so I just took it. So I would rather encourage this, about this much of simplification, I would rather encourage. It's elementary, and then also please note that 6x minus 2 becoming squared. See the pattern here? If you take the derivative once again, what do you think will happen? It's going to go over to 6x minus 2 to the third power, and so on and so forth. So you see some pattern. Okay, so much for the first problem, and let's go over to the second problem. This is another kind of problem that is okay. There are some second derivative problems that are either too trivial or really complicated, and these are two of the rare problems that turn out to be okay. Let's see, what's the derivative of this logarithmic function? Derivative of log of x is 1 over x, isn't it? So derivative of the outer function is 1 over and then times derivative of the inside. So what goes to the denominator? Derivative is 1 over x, so you have to get the same thing back. So y squared plus 3y y to the fourth power, Exactly the same thing has to come here. You see, inside doesn't change, so you just copy it. By the chain rule, you have to multiply the derivative of the inside, which is 4x to the third power plus 6y, it should be y. In the end, what do you get? 4y cubed plus 6y over whatever we had before, y to the fourth power plus 3y squared. So that's the derivative. By the way, if you take the derivative of this logarithm, usually inside goes down, and then numerator is the derivative of this inside. Maybe it's worthwhile remembering this form. Derivative of log of composite function is u prime of x over u of x, like this. By composite function, by chain rule, inside stay the same, and you have to multiply the derivative of the inside. But if you multiply something to fraction, the multiplication goes to the numerator. So it goes like this, and you can regard it as a formula if you prefer. Personally, I prefer to use it as a chain rule and go like this, and that is the first half of the problem. Let's go to the second derivative. Whoops. And now I don't see any logarithm anymore, so let's just go ahead with this problem here and just straight up quotient rule. So we need denominator squared, and then the numerator has to be u prime v minus u v prime. That's the structure, isn't it? So the derivative of the numerator, what is this? 12y squared plus 6, and then the denominator stays the same, and then the numerator stays the same, and finally the derivative of the denominator. Better increase fonts. Okay. So logarithmic function ended up giving you a fraction. Upon taking the second derivative, you have a quotient rule, rather typical for log functions. There can be more, but Second derivative problems can get very, very complicated very quickly, so it's going to be almost pointless in that point. And then for polynomial functions or something like that, it's too simple, so it's not really worth our time. These are some of those exceptional cases that fall in the intermediate, and the answer keys are here, like this, like that.